ask a question before you start?
Yes, please.
Is phase transition always accompanied by symmetry breaking or symmetry recovery?
No, no, not always. Um, and so, one example would be the transition between liquid and gas, right? So those are two phases that have the same symmetry, but there can be a first order transition between them, right? And so if you cross the phase boundary at low temperature, far from the critical point, then there's no symmetry change there. Uh, and so that's a counterexample.
Okay, thank you.
Right, right. Um,
I thought
right.
it was always accompanied by a phase transition, but I thought I didn't know there what was the symmetry broken for liquid gas phase transition, but there is not.
No, there isn't one. There isn't one. Okay, good. All right, so let's begin here. Right, and so in the class last week, we were talking about crystals, right? And at the end of the class, I spoke about an order parameter for crystallization. That is, in the change from a liquid to a crystal phase, the some symmetry is broken, right? That the liquid has complete translational symmetry. The crystal has only partial translational symmetry. The liquid has complete rotational symmetry. The crystal has only partial rotational symmetry. So there is some symmetry breaking associated with this transition. And so there ought to be an order parameter. And the order parameter should describe both the magnitude, that is, how much has the symmetry been broken, and something like the direction, that is, of all the possible choices of which positions to make special, what was actually selected. All right, and so a way to construct such an order parameter is to look at the density function. And so last week I drew some graphs of how the density function might look in a liquid, where it would be just flat, versus in a crystal, where it would have a series of peaks at the special positions. And so it could be written then, the density, as a rho of x is a constant plus some variation, a wave vector q times the cosine qx plus a phase phi. And the phase is what gives the information about where are the peaks. And so this rho q is the magnitude. And this is, well, what we could call the direction, right? That is, where are the peaks, right? It's the arbitrary choice that is made when going from the liquid to the crystal phase. Okay, and if we wanted to make the math look nice, we could combine these things and say the density is the constant plus a real part of some complex number, which is this rho q e to the I phi e to the I qx. And then this thing is a complex order parameter for crystallization. So here, the point of the complex number is just that it's a way of designing an order parameter that's the right type of mathematical object to do this job. Right? It's taking the type of order, which has both a magnitude and special positions, and putting them together into the right kind of quantity. And so a complex number is the right kind of quantity that can describe this sort of symmetry breaking. And later on, as we get into liquid crystals and other things, we'll see another example of trying to pick the right sort of mathematical object to describe whatever kind of order there is in a certain phase. Okay, so the transition from liquid, whoops, wrong pen, from liquid to crystal is a transition from this rho q equals 0 to rho q not equal 0 to some non-zero complex number with a magnitude and a direction. This rho q, by the way, it's an order parameter that describes the positional order. Now, as I pointed out to you last week, a crystal also has orientational order. Now, if it has positional order, then it automatically has some orientational order, the way that the crystal axes are pointing. And so this kind of an order parameter is fine to do the job of describing the transition from liquid to crystal. So we don't need to design a separate orientational order parameter now. We will later when we deal with liquid crystals. Okay, so that has to do with making the order parameter for crystallization. And so now is where I would ideally like to say, I'll design a little model like the van der Waals theory for the liquid gas transition. And I'll make a little model that describes the transition from a liquid phase to a crystal phase. Unfortunately, there isn't really a nice simple model like that out in the literature. So I don't have a simple story to invoke. It's more complicated than that. There are a lot of different types of crystals induced by a lot of different types of mechanisms. So I don't have a single simple story to show you, but maybe I should at least show you what phase diagrams typically look like. Okay, so let me sketch out a phase diagram in both the temperature pressure plane and the temperature volume plane. So in the temperature pressure plane, okay, if I want to make a phase diagram, let's see. So suppose we have temperature on the vertical axis and pressure on the horizontal axis. So we are accustomed to the liquid gas transition. Right? So that is a transition that is a diagonal line like this, where there's gas at high temperature, low pressure, and liquid at lower temperature and higher pressure. Now, the place where we would find a crystal phase is at even lower temperature and even higher pressure. Right? So the boundary between liquid and crystal would be a boundary that comes in like this. Right? So that crystal would be down there. And so you could get from liquid to crystal normally by reducing temperature or by increasing pressure like that. And then typically these two boundaries come together like this at a single point. And then beyond that, there is a direct transition from gas to crystal like this, or crystal to gas. The word for that, for going directly from crystal to gas, that is called sublimation. And the word for going from crystal to liquid, that is called melting. And the word for going from liquid to crystal is called freezing or crystallization. And I don't know if there is a word for going from gas directly to crystal.
Isn't it deposition?
What is that?
Deposition? Isn't that what it's called?
Deposition. Well, that is a process of starting with a vapor and depositing atoms onto a surface. I'm not sure if people would use that for the equilibrium phase transition. Okay, so this is a typical phase diagram. And so to identify a couple of special points, right, you remember this one is the critical point. That is where the transition from gas to liquid comes to an end. And this point here, where the phases come together, is called the triple point. Triple because it's the meeting of all three phases. You will see that these are two completely different kinds of points. These two kinds of points don't have anything to do with each other. So you don't want to get those things mixed up. Now, you might ask, is there a critical point for the liquid to crystal transition? Right? Is there a critical point at the end of this line? And the answer is no. Okay, so I will erase that. And this line rather goes on forever. And this is actually related to the question that Cheng asked just before class about symmetry changes across phase transitions. The point is that the liquid and the crystal phases have different symmetries from each other. That is, the liquid has this perfect translational and rotational symmetry, and the crystal doesn't. The crystal has some broken symmetry. Okay? And so if you are anywhere out here, right, you can say, well, does the material have these symmetries or not? Okay, that's a yes or no question. If the material has the symmetries of a liquid, it's a liquid. If the material has broken symmetries so that it no longer has all the liquid symmetries, then it's a crystal. Okay, so that's always a yes or no question. So there always has to be a boundary between liquid and crystal. You can only have a critical point between gas and liquid because gas and liquid have the same symmetry. So because they have the same symmetry, the differences between gas and liquid are just quantitative differences about what is the density. Right? And so you can go from a low density to a high density gradually, going around that way, or you can go from a low density to a high density abruptly when you cross a phase boundary. But it's a quantitative difference, not a qualitative difference, right? Whereas because this difference is a qualitative, symmetry-based difference, there can't be a critical point for that, right? That it has to always be a phase transition. Now, it might be a first order transition or a second order transition. Usually it's a first order transition, but sometimes it could be a second order transition. But either way, it is some kind of phase transition between liquid and crystal. Okay, so that is the phase diagram in terms of temperature and pressure. Okay. Now, we might also ask about the phase diagram in terms of temperature and volume, because we know that can be a little bit different, right? That when you specify volume or when you specify density, then there are two-phase coexistence regions, right? And so, we can try to figure out how does that look. So let me see if I can do that on the right. Okay, I'm going to erase a little bit to make more room. Okay, so if I want to make the phase diagram in terms of temperature and volume, okay, so this is volume per particle, or per atom, per molecule, whatever. All right. Well, what we know about is what's happening for relatively high volumes, that is, at relatively low pressures over here. Okay? So we already know about that thing. And so that is a boundary, something like this, between liquid and gas. Okay, so here is the critical point, which is at the same height as there, supposedly. Okay, that's TC, TC. Okay, so we know there is a gas phase out here and the liquid phase over there. Right. Now the crystal phase comes in at even smaller volumes, higher densities than the liquid. And so there has to be another boundary here. Okay, so here is the two-phase coexistence. Okay. And then there's going to be another boundary here with more two-phase coexistence, and then the crystal. So here we can draw two-phase coexistence between liquid and crystal. And then below this temperature, there's no more liquid. And so instead, we go directly between crystal and gas. So those lines represent the two-phase coexistence of crystal and gas. So here are the three phases that are expressed in terms of temperature and volume, in a way that corresponds to this kind of a chart. And so we can see over here, this is the critical point. And then the triple point, well, that's this whole horizontal segment right along here. This is where you could have coexistence of all three phases, crystal, liquid, and gas. Okay, so that's at this triple point temperature, the same as we see over on this side. Okay, so I'll mark this. That whole line is then triple point. Okay, so if you're anywhere in the coexistence region, well, I'll mark all of these lines mean coexistence. See, two-phase coexistence everywhere except right on that blue line. Okay, so up here, it's coexistence of liquid and gas. Here, it's coexistence of liquid and crystal. Down here, it's coexistence of gas and crystal. So, anywhere where you're in a two-phase coexistence region, you want to look to the right and look to the left. And you have coexistence of the phase that's over there on the right and the phase that's over there on the left, okay, with a volume that's given by what's the volume at this boundary, and a volume per particle that's given by what's the volume per particle at that boundary. So, if there were a homework problem that says, suppose you have this temperature and this volume per particle, you could figure out that you have a certain amount of crystal and a certain amount of gas, right? And you could solve the four equations in four unknowns to figure out how much crystal and how much gas you have, both by mass and by volume.
In real application, which one we can control easily, the pressure or the volume? Because all the time people express the phase diagram with temperature pressure relation, not volume. So which one we can control easily, the volume or the pressure?
That's a great question. I'm not sure there's a general rule for that. There are different types of experiments, and depending on what sort of situation you're in, it might be one or the other. I don't think I can give a general answer. Oh, I'm sorry. That's an interesting point. So I know, earlier you asked questions about analogous things in binary mixtures, right? So that what happens if you have mixtures of two kinds of substances, and there the thing that's analogous to volume would be, what's the percentage of each material, and the thing that's analogous to pressure is chemical potential, right? But in those experiments, you normally control the composition and you don't control the chemical potential. So it's easier to give an answer in that case. But in this case, I don't know. I can see experiments both ways. Okay, nice point, thanks. Okay, so those are some general comments about crystals. Okay. Now, I should mention that there are a lot of different kinds of crystal structures. And when you take courses about material science or about solid state physics, they really go through a lot of crystal structures in detail. I'm not going to be able to do that in this course, but I'll just show you a few highlights, okay? And then I can just show off some more Mathematica graphics. Okay, so I'm going to switch to Mathematica here. Okay, so I will share that. All right. So this is beginning with a couple of common crystal structures in two-dimensional systems. Okay? So one simple crystal lattice is just the square lattice. Okay? So here's an example of that. And you have to imagine this going on forever. Right? It doesn't, ideally, it doesn't really have boundaries along there. It just goes on forever in X and in Y. So here you can see that there is a fourfold symmetry, right? That there are special directions going horizontally and vertically, and you can rotate by 90 degrees to get from one to the other. And so everything is repeating periodically in position, you could regard this as a single square cell that gets repeated over and over again. That square cell in crystallography is called a unit cell. Okay. Here is another common crystal structure in two dimensions, commonly known as either the hexagonal lattice or the triangular lattice. You can hear either term for that. You can see that this structure has special directions here going horizontally and at plus 60 degrees and at minus 60 degrees. So it has a six-fold rotational symmetry. That is, you can rotate by 60 degrees and get back to the same kind of a structure. It keeps repeating periodically. The repeating unit of that is, well, I mean, there are different ways to define the repeating unit. One way to define the repeating unit would be a parallelogram like this one, right? That has an up-pointing triangle and a down-pointing triangle together. There are other crystals in two dimensions. These are just two common structures. Likewise, I will show you some three-dimensional crystal structures. Okay. This one is called simple cubic. It is, as the name suggests, just a simple cube, right? So here is a cubical unit cell, and it keeps repeating. Right? So here are 8 atoms at the corners of a cubical unit cell. And then we we could say, all right, there'll be another unit cell over here and another one in the front and another on the top, and it just keeps on repeating in all directions from there. This structure has cubic symmetry. That is, there are special directions along X and Y and Z. And you can rotate by 90 degrees about X or Y or Z to get back to the original structure. That is a very quick statement of what is very interesting group theory that I'm not going to talk about here. Okay, now there are other variations on crystals, on three-dimensional crystals that you hear about a lot. And I will just tell you two other common variations. Okay? So one that is shown here is a body-centered cubic. Body-centered cubic, which is commonly abbreviated as BCC. So what you can see in that structure is that there is this cubic unit cell with an extra atom right at the center of the cell, right? Surrounded by the 8 atoms at the corners. Now, this whole structure keeps repeating periodically, right? So this thing gets repeated in X and Y and Z, going off in all directions. So this is a variation, and it's not the same structure as the simple cubic. The symmetry looks similar as far as rotations go, but the nearest neighbor relations, here, the nearest neighbor atoms are from one corner to another. And here, the nearest neighbor atoms are from the center to any of the corners. And then one other variation is this one, which is called the face-centered cubic, commonly abbreviated as FCC. So this is a lattice where you have these 8 atoms at the corners of a cube, and then you also have an extra atom in the middle of every face of the cube, right? The face means the square side of a cube. And so here's an extra atom in the middle of the top face. Here's an extra atom in the middle of the front face. Here's an extra one in the middle of the side face. And then you can rotate around and you see that's true for all of the faces. One nice thing that we can do with three-dimensional graphics is look at the FCC structure from with the corner pointing up. Okay? And a nice thing about doing that is you can see there's then a plane of atoms here and a plane of atoms there. And within each of these planes, it looks like a triangular lattice. Okay? So if you put the FCC on its corner, you can see this aspect, which looks like a triangular lattice with multiple layers, right? So here's one triangular layer, then here's another triangular layer. And this atom is part of yet another triangular layer, and so forth. So the FCC could be regarded as a sequence of triangular layers, one on top of another one. This is, well, this is highlighted in my alternative picture right there, where I colored each of the triangular layers. And so here we have one in this kind of olive green and one in this purplish color. And then the blue is one atom in another triangular layer. Okay. So this is my 15-minute survey of what is a huge subject. And if you take a solid state physics course, they'll spend weeks going over this sort of thing. And there's a long list of crystal structures, which are all interesting in different ways. And there is an exhaustive catalog of all the mathematical possibilities, but I don't have time to go into that now. Instead, let me talk about one of the main considerations that determines which kind of crystal structure forms, right? So in general, there are all these different possibilities for crystal structure, and which possibility forms depends on the specific interactions between different types of atoms. Okay. So for some kinds of atoms, there tend to be preferential bonds in certain directions. For example, you might recall from chemistry classes that carbon tends to form bonds in a tetrahedral way, right? With one bond going up and then three more going down in the directions of a tetrahedron that is like a pyramid with a triangle at the base. That is a reason why carbon would tend to form a crystal that has a tetrahedral symmetry, like the diamond lattice. And similarly, other kinds of atoms have characteristic bonding patterns, and that influences the type of crystals that they form. And there are sometimes very complicated quantum mechanical calculations that determine what's this electron structure of different types of atoms in different types of lattices, and see what gives the lowest energy. Okay. That's a big subject. Now, there is one relatively simple version of that. Right? And the relatively simple version is that there are certain kinds of atoms or other particles that just tend to favor close packing. That is, for certain materials, the lowest free energy corresponds to the most efficient packing. That is, to the packing which gets the most number of atoms per volume. So we'll say the most atoms per volume, the least wasted space. So this would be true, especially if there are materials that have non-directional interactions between the atoms. So if the atoms would be like hard spheres. If the atoms are basically like hard spheres and they just tend to pack together, you want to get as many into a volume as you can. Right? And so in that case, there is a nice geometric argument to figure out what kind of lattice provides the most efficient packing with the least wasted space. Right? And we can figure that out based on a mathematical parameter called the packing fraction. So commonly written as phi, that is the volume that is taken up in particles divided by the total volume. Or for 2 dimensions, it's the area that is in particles divided by the total area. Here, I'll put like a parentheses around this. This is in 2D and this is in 3D. So let me show you what's meant by this parameter, both in 2 dimensions and in 3 dimensions. So here's an example in 2 dimensions. So this is the 2D square lattice. So, you saw an example with many disks packed together in Mathematica. Here's a close-up of 4 of them. Okay? So you can see that one cell is this big square right here. Okay. And then there's the next cell, which is the square. Well, I got cut off by the edge of my picture. That's strange. Okay, but then there's another cell over here, and another cell over here, and another one over there. And it just keeps repeating. Okay. So we could say that we can figure out the packing fraction by looking at a single unit cell. Okay, so this is a square unit cell. And that square contains 4 quarter atoms, right? Here's a quarter atom, like a quarter slice of pizza, right? And here's another quarter. And here's another quarter. And here's another quarter. Okay? So we could say that each square unit cell contains 4 times 1/4 atoms. That is, it contains 1 atom, all right, 1 disk-like atom. Okay, and then if we say that the spacing from center to center, that is this point to this point, is some distance a, then the radius of each atom the radius of each atom is A over 2. So the volume, or not volume, area, okay, the area in the particles, that is equal to the area of a circle. So that's pi r squared. So pi times A over 2 squared. So that's pi A squared over 4. Right? By comparison, the total area is the area of this unit cell, so the area of this square, of this area, right? And that is, well, the area of a square is A squared. So A squared. So if we combine those things, then we get the packing fraction phi, which is the area in particles. So pi A squared over 4 divided by A squared. So the A's cancel, and this is just pi over 4. Okay? And so that is approximately equal to 0.785. So this is telling us that if we pack the disks like this, then 78.5% of the area is used to contain atoms, right? That's the area that's in these blue regions. The remaining 21.5% of the area is wasted in between the atoms. That is this white space in there. Okay. So 78.5%, is that good or bad? Well, it depends what you have to compare it with. So let's compare it with something. Okay, how about this structure right here, which is the 2D hexagonal lattice. All right. Let's do the analogous calculation here. All right. So here, the unit cell is this parallelogram. Okay, so we could say how many atoms are in this parallelogram, right? The same kind of consideration that we had before. Well, let's look at that, right? So here, this looks like 1/6, right? It's, if we're slicing pizza, that's 1/6 of the pizza. Right? Here is 1/3. Here is 1/3. Here is 1/6 of a pizza. Okay, so the number of atoms in the unit cell, that is 1/6 plus 1/3 plus 1/3 plus 1/6. Oh, that's just equal to 1. Okay, so this adds up to 1 total atom per unit cell. The area that's devoted to particles is then the area of 1 particle. Right? So that is 1 times pi r squared. All right, so again, the radius is this A over 2. So it's pi A squared over 4. Right. Now, what about the total area? Right. Well, the total area is the area of the parallelogram, this thing. So we have to remember what's the area of a parallelogram. Ooh, that was high school geometry. Can any of you remember that far? Well, that is equal, whoops, wrong pen. That is equal to the base times the height. Okay. So the base is A. Okay. The height, that is this thing. Okay, so this angle is 60 degrees. So this hypotenuse is A, because this length is the same as this length. Okay. And so the height over here is a cosine 60, no, it's not, it's a sine 60 degrees, right? It's a sine 60 degrees. Yikes, what am I doing here? Eraser. A sine 60. And if you remember high school trigonometry, that's a root 3 over 2. Okay, so A times a root 3 over 2. Okay, so a squared root 3 over 2. So the phi for this case is equal to the area in particles, the pi a squared over 4, divided by the total area, that's a squared, not cubed, squared, root 3 over 2. So the a's cancel and we get this pure number, which is pi over 4 times 2 over root 3. So it's pi over 2 root 3, if I got that right. It's pi, oops, pi over 2 root 3? Yes, okay. So this is 0.907. Ooh, this is better, right? And we can see that this is better, right? This looks like a more efficient packing than this one, just in terms of how much white space is there between the particles, right? It looks like the square unit cell has more wasted white space, and this has less wasted white space. And, you know, when I was a kid, I would sometimes do things like arrange coins on a table and see how could you put coins together in the most efficient way. And it would make a picture like this one, right? And so maybe some of you have done that too. This actually is the most efficient packing in 2D. So there are mathematical proofs of that. All right, so if we have a two-dimensional material that tends to form a close packed structure, we would expect then to get a hexagonal crystal and not a square crystal. Okay. Now, what about in 3D? How am I doing on time? Oops, I'm out of time. I'm going to stop talking for now. Okay, I have to stop. So I will do 3D in the next class on Wednesday. All right, and so at least I'll do one example of that. So I will stop for now and I'll see you guys on Wednesday. All right, but I'll stick around to answer questions if anybody has any. Thanks, bye.